Picture this. You're standing at a port, looking out at the ocean, watching a massive cargo ship just bulldoze its way through the water. It's a pretty common sight, right? But here is an absolutely incredible engineering paradox. We have actually known exactly how to make boats literally fly over the surface of the water since 1919. Yeah, 1919. So why, over a century later, are these colossal cargo vessels still just pushing through the ocean the exact same way they did 100 years ago?
Well, that is the exact mystery we're diving into in this explainer. Why don't cargo ships fly? The reality of this technology is staggering. Right now, we have submerged wing systems that can lift a 40-ton ferry completely out of the ocean, just suspending it in mid-air above the waves. It's wild to see. But as we'll discover, there's a $2 billion mathematical limit that ruthlessly killed the commercial cargo hydrofoil before it could ever really change global shipping.
To really understand why this matters, we have to look at a conventional displacement hull compared to a hydrofoil. A standard displacement hull pushes a continuous, heavy wall of water at around 14 to 18 knots. A hydrofoil, it skims the surface at 45 knots with 80% less drag. You know, it's kind of like dragging a dinner plate through a full bathtub. If you pull it flat against the water, the resistance is enormous. It fights you the whole way. But if you lift that plate so only the very rim touches the surface, the resistance basically disappears. That's the hydrofoil principle in a nutshell. But what happens when that fragile little rim hits a submerged log while doing 45 knots? We're going to get there shortly, because that tension between incredible speed and serious physical danger is exactly what makes this tech so fascinating.
Okay, let's move into part 1, deconstructing the flying boat.
Okay, let's dive into this. There's this persistent myth that if you want a massive ship to go faster, you just need to bolt on bigger engines. But water resistance is an unforgiving physical wall. You can't just push harder to go faster. The water wins that argument every single time. And this brings us to the brutal geometry of marine flight, the square-cube law. So lift scales by the square of a foil's dimensions. That means if you double the wing size, you get 4 times the lift. Sounds fantastic, right? But wait, look at the second half of that equation. The vessel's weight scales by the cube. If you double a ship's dimensions in every direction, the weight actually increases by a factor of 8. So as a ship gets bigger, its weight multiplies way faster than the wing's lifting power. And because of this math, the concept fails before a single rivet is even placed. Look at the 50,000-ton scale of a serious cargo ship. This geometry becomes an absolute death sentence. To lift a ship that heavy, the submerged wings would mathematically have to be physically larger than the ship itself. There's just no way. The cargo hydrofoil was completely doomed, not by bad engineering, but by pure, unbeatable geometry.
Which brings us to part 2, the mechanical X-ray. Let's take a look under the surface. So, while massive cargo ships couldn't fly, smaller passenger ferries absolutely could. To see the physics trick that keeps them from crashing, we have to talk about Bernoulli's principle. As water flows faster over the curved upper surface of the wing, it creates a low-pressure zone, which generates enormous upward lift. And here's the real secret. Because liquid water is roughly 800 times denser than air, a tiny submerged wing can generate massive, immense lift using the exact same aerodynamic principles as an airplane wing. It's basically an airplane just flying underwater. But once that hull actually lifts clear of the water, a whole new problem pops up. The boat totally loses its natural hydrostatic buoyancy. To stay upright, it has to constantly battle 6 degrees of freedom: surge, sway, heave, roll, pitch, and yaw. Once it's foil-borne, a ferry really isn't a boat anymore. It behaves much more like a fighter jet, requiring constant, split-second adjustments just to stay level in unpredictable seas. Now, what's really interesting about this slide is how engineers tackled this crazy instability. They went in 2 completely different directions. The first is passive V-shaped foils, like the ones on the Soviet Raketa. These are rugged, surface-piercing wings that use their actual physical geometry to naturally self-correct when the boat tips. Pretty clever. Contrast that with the active T-shaped foils of the Boeing jetfoil. These are fully submerged and rely on highly complex radar altimeters and computers to adjust their flaps multiple times a second. It's a literal mechanical ballet happening right beneath the waves.
But all of this brilliant engineering runs headfirst into a massive hurdle: the cavitation barrier. As you push these foils to 45 or 50 knots, the fluid pressure over the wing drops so incredibly low that the water literally vaporizes into unstable cavities. It just boils.
And when these vapor bubbles collapse, they do so with violent shock waves that can physically erode solid metal and completely destroy your aerodynamic lift. It is a hard physical speed limit of the ocean, basically a brutal underwater equivalent to the sound barrier.
And that leads us perfectly into part 3, the ocean's brutal reality.
Between the highly complex control systems and that cavitation barrier, operating these vessels was always a delicate balancing act. But ultimately, it was the ocean's revenge that killed the hydrofoil boom. First off, the water is never clean. Hitting a submerged piece of driftwood at 45 knots isn't just a bump. Actually, scratch that, it's a massive structural event that transmits highway speed impacts directly into the hull. Second, you've got invisible biological fouling. Things like barnacles slowly destroy the wing's pristine shape, completely ruining the lift and fuel efficiency. And finally, in rough waters like the Hawaiian channels, the active computer systems tried to rapidly contour over large waves. The result? Severe passenger seasickness that doomed entire operations like Hawaii's sea flight. I mean, a marvel of engineering is totally useless if every single passenger steps off feeling completely miserable, right?
And this brilliantly illustrates what happened next. Because of all these operational nightmares, a simple, rugged disruptor took their place on commercial routes, the catamaran. By just splitting the hull into 2 narrow sheets, the catamaran offered moderate drag, shallow drafts, and total immunity to those deep debris strikes. It essentially matched hydrofoil speeds without the extreme maintenance or complex hydraulic systems. The simple, rugged disruptor had won, and the hydrofoil just kind of faded away.
But wait, here's where it gets good. Part 4, the electric foiling resurgence.
The whole narrative around hydrofoils has completely shifted today. And ironically, it's the massive weight of modern electric batteries that is bringing this seemingly dead technology back to life. The magic number here is 80%. When you're trying to build an electric ferry, the battery pack you need is incredibly heavy. If you try to push a heavy, conventional hull through the water, you're going to drain that battery instantly. But by reducing drag by 80%, marine flight is no longer just a luxury for a cool, smooth ride. It is an absolute economic necessity. To make electric ferries, like the modern Candela P12, actually viable, they literally must fly. Otherwise, they'd require impossibly heavy batteries and massive shoreside charging grids that just don't exist.
And hey, what about that destructive cavitation barrier we talked about earlier? Well, modern engineers are using artificial intelligence to completely defeat it. Teams like SB80 have designed these radical, ventilated wedge foils. Instead of trying to avoid the vapor cavities, these new shapes intentionally inject air to create a stable cushion right behind the wing. It's genius. This entirely solves the 20th century cavitation problem, allowing safe, stable flight at mind-bending speeds.
So how fast are we talking? Well, 65.45 knots is the current world sailing speed record. That's a speed where the laws of physics really start to bend. But with these new AI-designed ventilated foils, the SP80 team isn't just trying to gently beat that record, they are aiming to utterly smash it by hitting an unprecedented 80 knots. It's this thrilling new frontier for fluid dynamics that is pushing the very boundaries of what is mechanically possible on the water. Finally, let's wrap this up with part 5, the final economic answer. So the crucial point is we can now resolve the mystery of why the hydrofoil vanished and exactly why it is returning. It's a 3-phase evolution. First, back in the 20th century, cheap fossil fuels allowed displacement boats to just inefficiently bulldoze their way through the water. Efficiency just didn't matter enough when fuel was that cheap. Second, catamarans came along and offered rugged simplicity that easily beat out the mechanical headaches of early hydrofoils. But today, step 3 changes everything. Modern battery weight limits mean we can no longer afford to just bulldoze water. The hydrofoil didn't fail due to bad engineering. It was just temporarily defeated by the cheap economics of fossil fuels. So, the paradox is solved. This resurrected engineering marvel is now absolutely essential. Not only does it provide predictable, high-speed, zero-emission public transit, but by flying over the surface, these vessels create near-zero wake. That is huge for protecting delicate coastal ecosystems from erosion. It is just a brilliant blend of hidden mechanics and modern necessity.
Which leaves us with this final provocative thought. If heavy electric batteries were the exact key needed to resurrect the failed technology of marine flight, what other discarded engineering marvels of the past are just sitting there, waiting for the green revolution to bring them back to life? Thanks for diving into the mechanics of the hydrofoil with me today. I absolutely invite you to discover more engineering mysteries with us in future explainers. Catch you next time.